Hi guys, imagine you are an equity analyst trying to forecast a company revenues. Advertising spending matter, but so do interest rates, consumer income, inflations, and seasonalities. So here are the questions: how do professionals figure out which factors actually matters? And which ones are just creating noise? This is actually why multiple regressions exist. So let's begin with the intuitions. Very few things in finance are driven by just one factors. Take stock returns. They don't depend only on interest rate, but depend on inflation, economic growth, investor sentiments, company earnings, and dozens of other variables. The same idea applies everywhere. House price depend on locations, size, school qualities, crime rates, and mortgage rates. Company sales depend on advertising, consumer income, competitors, and product prices. So, if we only study one variable at a time, we are missing small of the stories. Multiple regressions solves this problem. Instead of asking the advertising affect sales, it asks how much the advertising affects sales after controlling for income, inflation, and every other important factors. That single phrase, holding everything else constant, is what makes multiple regressions so powerful. It allows us to isolate the effect of one variable while keeping the other fixed. That's why economists use it. Now let's formalize the idea. A multiple regressions model looks like this. Y equals beta 0 plus beta 1 times x1 plus beta 2 times x2 plus beta 3 times x3 plus an error term. Don't let the equation intimidate you. Think of it like a receipt. The dependent variable y is what we are trying to explain or predict. Maybe it's a company sales, maybe it's a stock returns, maybe it's a GDP growth. Each X variable represents one possible influence. Advertising spending, interest rates, consumer income, exchange rates. The beta coefficients measure how sensitive Y is to its factors. And finally, the error terms captures everything the model cannot explain. No model is perfect. There will always be unexpected events, measurements, error, or factors we simply forgot to include. For example, a retailer predicts monthly sales using advertising spending, consumer income, inflations. Regressions estimates how much each factors contributes while controlling for others. So management can identify which variables truly drive sales instead of relying on intuitions. So now comes on an important questions. How do we know whether our regressions is actually doing a good job? The answers begins with anova, analysis of variance. Image on the variations in sales. Some months sales are high, some months they are low. ANOVA asks one question: how much of that variations can our model explain and how much remains unexplained? The total variations is called SST. the total sum of squares. ANOVA split into two pieces. First is RSS, regression sum of squares. This is the variations explained by the model. The second is SSE, sum of square errors. This is the variations the model fails to explain. And the relationships is very simple. XST equal RSS plus SSE. Every bit of variation either gets explained or it doesn't. One of the first statistics everyone looks at is R squares. R squares simply measure the percentage of total variations explained by the regression models. Suppose R squared equals 0.8. That means 80% of variations in the dependent variable is explained by the independent variables. But R squared has a weakness. It almost never decreases when you add more variables. Even less variable can make R squared look slightly better. Image predicting house price. You already use size, locations, and age. Then you add today's temperature or the number of letters in the homeowner's name. Those variables probably don't belong. Yet R squared may still increase a little. That's why professionals often prefer adjust R squares. Adjust R squared rewards variables that generally improve the model, but it penalizes unnecessary complexity. In the other words, it asks whether the additional variable earns its place. This makes adjust R squared much more useful when comparing the model with different numbers of independent variables. For example, model A uses 3 variables, model B uses 8 variables. Both have R squared equals 0.85. But model A has higher adjust R squares, so the extra 5 variables add little value but increase complexity. Suppose two different analysts build two different regression models. Which one should you trust? This is where AIC and BIC becomes useful. So AIC, the archive information criterions, focus on forecasting performance. If your goal is predicting future stock returns or future sales, AIC is usually preferred. So BIC, the Bayesian information criterions, place a stronger penalty on unnecessary variables. Its goal is finding the model that best explains the data while remaining as simple as possible. So a useful way to remember this is AIC like predictions, BIC like simplicity. So far we look at individual variables, but sometimes we want to evaluate several variables together. Imagine your full model includes 4 explanatory variables. Now suppose you remove 2 of them. Has the model actually become worse, or were those variables unnecessary all along? This is exactly what the joint F test answers. The null hypothesis says the exclude variable provides no additional explanatory power. The alternative says at least one of them improves the models. If the calculated F statistic exceeds the critical value, we reject the null hypothesis. That means the exclude variable collectively matter and should remain in the model